Our next speaker today is Kelli McCoy. Kelli McCoy began her career at NASA Kennedy Space Center as an industrial engineer in the Launch Services Program following her graduation from Georgia Tech with an MS in Industrial and Systems Engineering. She went on to obtain an MS in Applied Math and Statistics at Georgetown University and subsequently developed probability models to estimate cost and schedule during her tenure with the Office of Evaluation at NASA headquarters. Now at Jet Propulsion Laboratory, she has found applicability for math and probability models in an engineering environment. She further developed that skill set as the lead of the Europa Clipper Project Systems Engineering Analysis Team, where she and her team produced 3 probabilistic risk assessments for the mission using their model-based systems engineering environment. She is currently the modeling lead for a JPL New Frontiers proposal and is a member of JPL's Quantification of Uncertainty Across Disciplines Quad team, which is promoting uncertainty quantification practices across JPL. In parallel, Kelli is pursuing a PhD in UQ at University of Southern California. Co-author Roger Ghanem is a professor of civil engineering at the University of Southern California. Please welcome Kelli.
Thank you guys for coming today. I'd also like to acknowledge another collaborator in the room, Mike DiNicola, who's working closely with me on this as well. So we've heard a lot over the past few days about different methodologies, statistical methodologies and otherwise that we can use to improve test design. And this particular talk is going to address using those techniques in a space formulation environment. So we get in early. We try to do analysis that helps inform the design and helps us make better decisions in our design process early and hopefully yields better performance on the back end. So just some terminology, and we're probably all familiar with it, but I know agency to agency, center to center, we use terminology slightly differently. So systems engineering, of course, is cross-cutting engineering function that focuses on designing, integrating, and managing complex systems over the whole life cycle. And like I said, we're going to talk specifically about early mission formulation, space mission formulation. And then UQ, of course, is exploring the unknown, basically, using probability and statistics. And so how do we blend these two to ultimately make better decisions? So that's kind of what we're going to go through today. And at JPL, we want to use these techniques to stabilize baselines early, or maybe leave them open if we don't know enough to make good decisions yet. We want to inform requirements statistically, understand our risk, and balance that with cost, schedule, other technical parameters that may be at play. And so we do this through UQ infrastructure, acknowledging the variability inherent in our systems and models of those systems. So how does a space mission come to bear? Well, usually there's been some science phenomenology that's of interest or has been discovered through a previous mission or another maybe ground-based telescope or other ground-based source. And the application I'm going to talk about is Enceladus. So Enceladus, for those of you not familiar with your outer planet moons, it's I know I wasn't. So it's a moon of Saturn, a smaller moon of Saturn that has geysers shooting out of it. And what's unique about Enceladus is it's got a really thick ice sheet. And by observing these moons through the Cassini spacecraft that was launched in the late 90s, observed Saturn and its moons over a couple decades until 2017, we were able to see that Enceladus was particularly interesting because these plumes potentially have ingredients for life. So not that we're expecting to find whales or something under the ice surface, but it could be a habitable environment in that ocean. So we want to go back. We want to study that. We want to understand the nature of this ocean and whether or not it could potentially host life. So we have this data from Cassini. It flew past Enceladus through these plumes, kind of on this path that you see in the bottom left here, over what we call tiger stripes. So these tiger stripes are in blue. and we fly across them and we collect composition information, particle counts as we fly through these. And so subsequent to the Cassini mission, scientists have built physics models of what this generating process might look like. These plumes erupt out of the surface. This is a notional picture of kind of a conical boundary value problem that's been established as one of the physics, potential physics propagator, that's ballistic particle propagator that we're going to talk about shortly. So we need to use these physics models to inform a future mission. We need to use the limited data that Cassini was able to capture by flying through the plumes and build a new mission that's going to go specifically to study habitability of this particular body. And there are a lot of risks involved in this. So we don't know exactly, for example, how the velocity of these plumes coming out. So if these particles are big, hypervelocity ejection process, then we could have to worry about things like micrometeorites puncturing our propulsion tank, for example. So things like that we need to think about as we design. So what does this look like? So we made many observations of this moon, but we were only able to get 2 samples that we can really pin down of ice particle grains. So we have 2 flybys of Cassini, one at 100 kilometers, one at 50 kilometers. And what we have are particle counts bin by range particle size. And we are interested in collecting a specific mass. So we need to understand how our particle counts by bin size, which is in this upper right table here, how we can translate that into mass. So assuming a spherical volume and a density of ice, we can get to a range of mass that this HRD Cassini instrument saw. So again, we have this physics model built by scientists that assumes a ballistic particle propagator is the appropriate physics here. There are others under consideration, but for simplicity, we'll talk about that one. And it takes some input data and it propagates ice grains to an altitude that we're interested in. So this model, while it's one of the simpler physics models that could be brought to bear on this problem, is computationally intensive, like we've heard a lot of people talk about. So how do we deal with that? So in this particular case, we're going to use polynomial chaos expansion, PCE, to help us build a surrogate model so we can look at a lot of interesting properties going on here and do it quickly. So we have distributions that, of course, we're feeding into this model, and we wish to do a better job understanding what those distributions should be. So we use Bayesian inference, and specifically, we're going to use approximate Bayesian computation to try to avoid computing a likelihood function. So once we have an updated data, for example, we can use this to input to the model and estimate mass that we would collect. So now that we have a model that we trust, we can start to make different trades on where to fly through these plumes. So is it best to fly horizontally, like in this picture? Which jet might be contribute the most mass production? And might we want to fly over that or target that? And that has a lot of system implications, because if you want to target a specific jet, you need more delta V, you need a more expensive attitude control system. These particular things propagate through your system and system cost and system risk. So just diving slightly deeper into the techniques used here. I mentioned approximate Bayesian computation. So we want to approximate the likelihood function through simulations, and we want to compare those outcomes to observed data. So we get a candidate posterior sample, and we're able to say, is this sample too different from the data? And if it is, we reject it. And so we get a very simple likelihood function for this problem, and then we can execute Bayes' theorem in the way that you traditionally see it posed. We also use polynomial chaos expansion, as I mentioned, to create a surrogate physics model. And so with this, we can do a lot. With a polynomial, you can start to take derivatives. You can start to understand the contributions of your variables to your variance. Solvencies, things like that. So we do that here, and specifically, we use our Hermite polynomial basis function with a Gaussian germ here. And what's unique about this problem, through the Cassini mission, we were able to isolate 100 different jets along the surface, and they're all a little bit uncertain of where they are. Definitely uncertainty on which direction they could be pointing. In other words, which direction the material is ejecting. So we have a high dimensional problem, and we're able to express that with each jet by looking at parameters that are unique to each jet. So where it is and what direction it's pointing. And then we have some common parameters that we're able to address here as well. And so we're able to simplify that through this PCE. So these are the two primary techniques that we're exploring for use on this problem. So now, how do we take these techniques and inform risk and inform design? So, we start with these N by N joint density comparisons, start to understand the relationship between our variables, understand our relationship with our quantity of interest. Are there linear, nonlinear relationships between these, which might we want to study further because they're contributing most to the results. Through the parameter inference process, we're able to understand what size particles might be there and in what mass they might produce. So, for example, we're worried about small particles because they might clog our instrument. Ability of these particles being present and how much mass might we be dealing with if we just think about those particle sizes. As I already mentioned, we're worried about large particles because those could pose a safety concern for our spacecraft. So can the instrument suite accept these types of mass flow rates for certain particle sizes? Or will they be coming out so quickly that we need to consider dead time? So these are design considerations that kind of flow out of this analysis. Another design consideration is the mass that we could collect for a given collector size. So we're going to fly through these plumes. We're going to have a collector that's counting particles, measuring mass as we fly through. What size does that collector need to be in order to meet our requirements? Generally speaking, we collect more with a larger aperture, but this comes with mass constraints, other constraints that we need to consider that might impact our system. So we're also questioning where we should mount this collector. So should we mount it in the ram direction? So as we're flying through, it's going in the direction of our velocity, or should we mount it in a nadir position where it's kind of looking down? And so, so we can think about, what is the average mass we might collect? We might think about, if we have a requirement on mass, what's the probability that we exceed our requirement for a given mounting position for the collector? So these are all, again, questions that we need to use this infrastructure to understand. So as far as the polynomial chaos expansion, we want to use that to support trajectory design. So we want to understand, how should we fly? Where should we fly? How low should we fly? Should we target a specific jet that might be producing more? So we construct this surrogate PCE, again, that closely replicates the higher fidelity physics model. And we're able to look at which of these jets is contributing most for a particular flight path. And so we're hoping in flight that we can start to use this infrastructure to learn as we fly. And then later in a subsequent flyby, target a jet that's producing maybe more than another. So sort of update this PCE as we fly and learn from it. This box plot here in the bottom right is really looking at flyby by flyby, altitude by altitude, how much mass can we get? And so these lower altitude flybys are collecting more mass. So this call out box is pointing to jets 14, 16, and 18. We get more mass if we target a specific jet. In other words, we fly right over it. But that means we have to expend a lot of propulsion, a lot of delta V. We have to have a very sophisticated attitude control system on board that we target that specific jet. And so is that worth it? And what's interesting about that strategy is that from an orbital mechanics perspective, when you come around on the subsequent flyby, you'll see the mass drop significantly in the box plot for flyby 15. And that's because you're reorienting and you're flying kind of between two different jets. So is this observing strategy better than one where you just stay at higher altitude, you don't target a jet, you have a cheaper attitude control system, less delta V? So these are all traits that you can start to make if you have an infrastructure like this in place really early in your design cycle. So to kind of close out here, we're at JPL, we're trying to leverage these techniques earlier. And we're trying to do this through our systems engineering organization. And so this hopefully sets us up for better V&D procedures, better requirements development, better risk management, higher reliability, and we can hopefully start to make better decisions again earlier, leave these decisions open where it makes sense, and yeah, just have a better engineering process as a whole. Any questions?
You guys are using PTE in some of these surrogate models. What are your thoughts on using that as opposed to something else?
You know, that's there are a lot of different things I think you could explore for a surrogate model, and that particular technique is one our research group embraces. We've done a lot of work on projection pursuit, which is kind of another segue off of PCE where you can reduce the dimensionality, run faster, things like that. So we haven't looked at other surrogate types of models for this problem, just PCE, but we have looked at, you know, what's the best way to implement PCE for this problem.
What's your input and output dimension?
I'm sorry.
What's the input and output dimension?
So I think we're going in with 607 dimensions, and I want to say coming out with under 100. Can't recall.
Thanks.
Sure.
What are your barriers to adoption in terms of has all been totally smooth? Everybody just totally bought into it. Yeah, great idea. Let's go do that. How's that going?
Do you mean as an organization, JPL organization, or on the particular project itself?
Take that one.
All right. So I would say that the barrier to entry at JPL has been high. There's been resistance to these types of techniques in systems engineering for whatever reason. And so, you know, we've really had to push and show value, demonstrate value of these techniques. The individuals on this particular project are very excited about these types of approaches. They see the value in them. They like that it inherently acknowledges the risk that's there that we've been ignoring through these deterministic processes. So I think there's more work to go on the culture of JPL and infusing these on our early project designs, but project by project that you're seeing more and more adoption.
A follow-up question, if you don't mind?
Sure.
What mechanisms are you using for coalition building?
So we've actually collaborated quite a bit with Sandia, and we rolled out training to the workforce, partnering with Sandia. Myself, Mike, and Melissa here, we do some roadshows, so to speak, for our particular systems engineering organization. So right now it's been a lot of training, word of mouth, and trying to show results. So when we get a success story like this, hopefully will be the success stories we had on Europa Clipper. We try to socialize those. So it's been kind of a proving your worth type of strategy. Any other questions?
Maybe a more general question.
Sure.
I think it was on your second slide, you were defining uncertainty quantification. And it said something like it's a measure using probability and statistics. And that's typically how I think of uncertainty quantification as well, but I don't think I'm curious, are there ways to do uncertainty quantification without, grounding yourself in probability and statistics? This is something that people have come to me and kind of like ask me about. And I'm like, I don't probably, but I don't know how to decide of like probability.
No, that's fair. And this is my definition, by the way. It may not be a textbook definition, but I think that probability and statistics is the only method I know of that helps us acknowledge risk. And there may be some other offshoots, but I don't know of a methodology or a framework that can quantify uncertainty besides probability and statistics. That makes sense. I'm sure someone can argue with me on that. But if you introduce deterministic methods, to me, you're in the realm of machine learning or some kind of deterministic optimization and not quantifying uncertainty. That's all personal opinion, I guess. But